In this section, I'm going to go over how to graph a quadratic function in standard form. Now, standard form is the form y equals ax squared plus bx plus c. And when a quadratic function is in that form, it's not obvious where the vertex is. Now, in the last section, we learned how to graph a quadratic function in vertex form, and it was pretty clear where the vertex was in that case. But in this case, we have to be a little clever on how to find the vertex. Now, one way to find the vertex is by using symmetric points. And symmetric points are points on a quadratic function that have the same y-coordinate, like those two there, 0, 9, and 10, 9. And you see they're symmetric because they're across this axis of symmetry here that goes right through the middle of the parabola. And on this other one, we have the points -14, 5, and 3, 5. Those would be called symmetric points. Again, their y-coordinates are the same. They're both 5. Now, if we know two ordered pairs that are symmetric on a parabola, we can find the x-coordinate of the vertex by averaging the two x-coordinates of the symmetric points. So in this first one, for example, the x-coordinate is 0 for the first one and 10 for the second one. So we just average 0 and 10, meaning take 0 plus 10 and then divide by 2. So that would be 10 divided by 2, which would be 5. So that would be the x-coordinate right here, 5. So x equals 5. Now the y-coordinate you can find by just plugging that x back into your original function up here for x, right here, and finding y. So once we have the x-coordinate, we can really find the whole ordered pair. In this other example, again, the x-coordinates are -14 and 3. So if we average those, -14 plus 3 over 2, that'd be -11 over 2. So that would be -5.5. And you're finding that x-coordinate is -5.5. And that would be this x value right there on the graph. Now you can use any two symmetric points you want. Notice on this first example we used the y-intercept along with a symmetric point that corresponds to that. And in the second example we just used two arbitrary points. And you could even use the two x-intercepts if you wanted to, because x-intercepts will always be symmetric points because they both have a y-coordinate of 0. So any pair of symmetric points would work for this. So even though it works to use any pair of symmetric points, the ones that are usually the easiest to work with are the y-intercept along with its corresponding symmetric point. And I'll show you why in just a second. So let's look at an example. We're going to use symmetric points to graph y equals x squared minus 4x plus 5. Now first, let me start by finding the y-intercept. So to find the y-intercept, all we have to do is substitute a 0 in for x. So when we substitute 0 in for x, we get 0 squared minus 4 times 0 plus 5. So y equals 5. So the y-intercept is 0, 5. Now I'm going to find another point that's symmetric to the y-intercept. Now since it's symmetric, it's going to have the same y-coordinate. So I'm forcing the y-coordinate to be 5. So I'm going to substitute a 5 right in here for the y-coordinate. And when I do that, I get the equation 5 equals x squared minus 4x plus 5. Now the nice thing about this equation is I can subtract 5 from both sides, and it's going to drop out, and we're just going to get 0 equals x squared minus 4x. Now this expression on the right can be easily factored because there's no constant term, so we just pull out the x as a common factor, and we get x times x minus 4, and then we set each part equal to 0, so we would get x equals 0 and x minus 4 equals 0. and the second part solves out to x equals 4. So we get these two solutions. So that's telling us that the y-coordinate will be 5 when x equals 0. Now that shouldn't surprise us because that's the y-intercept that we already knew. And the other one is x equals 4. So those are the, in other words, the symmetric point that we were looking for would have an x-coordinate of 4. So it would be 4, 5. So these 2 points right here are symmetric points. They both have y-coordinates of 5. And if we average the 2 x-coordinates together, now the x-coordinates are 0 and 4. So if we average those 2 numbers together, we'll get the x-coordinate for the vertex. So for the vertex, the x-coordinate will be the average of 0 and 4. So 0 plus 4 over 2, which is just 2. Now once I know x is 2, I can just substitute that back into the original equation for the x to solve for the y. So the y would be 2 squared minus 4 times 2 plus 5. So y is going to be 4 minus 8 plus 5, which would be negative 4 plus 5, so it would come out to be 1. And so the vertex would be the ordered pair 2, 1. Okay, so we found the x-coordinate by averaging the 2 x-coordinates of the symmetric points, and then the y-coordinate for that just by plugging it back into the function. Now we can graph this function pretty easily. We'll just plot the vertex. So 2, 1 is right here. And we'll plot the 2 symmetric points. So 0, 5, that's the y-intercept. And then 4, 5 is the one symmetric to it. And just with those 3 points, we get a pretty good picture. We know the vertex is where it turns, and that's right here. And then we have these 2 points to kind of guide it. So the graph is just going to come down here, and it's going to turn and then go back up. Now if I use this procedure on a general quadratic function, I can derive a formula which will make it even easier for us to find the vertex when it's in standard form. So let's assume we're just starting out with some general quadratic function, y equals ax squared plus bx plus c. Now the y-intercept for that is going to be 0, c. Because if we substitute a 0 in for x, we just get a y value of c. So 0c is the y-intercept. So if we want to find the symmetric point that's across from that 0c, we know that the y-coordinate would still have to be c, so we'd substitute that in for y, and we get c equals ax squared plus bx plus c. And then we can subtract c from both sides, and that cancels out just like it did when we had a number in there. And then on the right side of the equation, since there's no constant term, x is a common factor, so we can factor that out, and that leaves us with ax plus b. And then we set each part equal to 0, so x equals 0 and ax plus b equals 0. And then when we solve the second one, we get ax equals negative b, so x equals negative b over a. So that means the symmetric point would be negative b over a, comma c. So these 2 points are symmetric points. They both have y-coordinates of c. And so to find the vertex, we would have to average the 2 x-coordinates of those points. So the x-coordinate of the vertex would be 0 plus a negative b over a divided by 2. And so that's just negative b over a divided by 2. And that's the same as saying negative b over a times the reciprocal of 2, which would be 1/2, which is negative b over 2a. So that's the formula that I was trying to derive. And you see that comes just from that same process that we were using, getting two symmetric points and then averaging the two x-coordinates of those symmetric points. And the x-coordinate of the vertex will always be negative b over 2a. Let's see if we can use that formula on this example. We want to graph y equals x squared minus 8x plus 7. Now first of all, let's determine what a, b, and c are. Now a is the coefficient in front of the x squared, and since there's no number there, it's assumed to be a 1. So a is 1. And b is the coefficient in front of the x, so b is negative 8. And c would be 7, the constant term. And according to our formula, for the vertex, the x-coordinate of that vertex will be negative b over 2a. Now b is already negative, so we really like to think of negative b as meaning the opposite of b. So think of this negative b meaning the opposite of b. Because if b starts out negative, you're taking the negative of a negative, which makes it positive again. So in this case, that's really positive 8 over 2 times 1, which is 8 over 2, which is 4. So x is 4. Now, to find the y-coordinate, we'll plug that back into the original function where the x is, in both places. So y would be 4 squared minus 8 times 4 plus 7. So that would be 16 minus 32 plus 7. And so that would be negative 16 plus 7, which is negative 9. So if we put those two things together, the ordered pair for the vertex would be have an x-coordinate of 4 and a y-coordinate of negative 9. So that's the key point on the graph. That's the vertex where it turns. Now the other key points that we usually want to include are like the y-intercept. So to find the y-intercept, you substitute a 0 in for x. So in this case, you would just get y equals 7. So the y-intercept is 0, 7. So that's a point we could include on the graph. And sometimes we like to also find the x-intercepts. Let's do that this time. And to do that, you plug a 0 in for y in the original function. So you have 0 equals x squared minus 8x plus 7. And then you solve this by factoring. So if you factor the right side, you get x minus 7, x minus 1. And when you set both of those equal to 0, you end up with x equals 7 and 1. So those are the x-intercepts. That's telling you where it's going to cross the x-axis. You'd actually have 7, 0 and 1, 0 as your ordered pairs. So now let's graph this function using this information. So we had found that the vertex was the ordered pair 4, negative 9. We had the y-intercept to be 0, 7. And we found the x-intercepts to be 7, 0 and 1, 0. And so if we plot that information, let's start with the vertex at 4, negative 9. So that would be right here. And then let's do the y-intercept, 0, 7. So that's way up here. And then the x-intercepts are 7, 0 and 1, 0. And you can kind of see how this is coming together at this point. This point at the bottom is the vertex, so that's where it's reaching a minimum point and turning around. These two x-intercepts are actually symmetric. They're the same distance on either side of the center line. And you're also going to have a symmetric point corresponding to this. Now, if you think about this carefully, the axis of symmetry comes right up through the middle where the vertex is. And this point here on the left the y-intercept is, if you count the number of spaces from the center line, it's 1, 2, 3, 4 spaces to the left. So if you go 4 spaces to the right, you're going to have another point right here. So you can go ahead and plot that too, which will kind of round your graph out. So that's the symmetric point corresponding to the y-intercept. And then we'll just connect these with a nice parabola shape. So it comes down, reaches a minimum, comes back up. Now usually if you graph the vertex and the y-intercept and the x-intercepts, you usually get a pretty good picture. But you also can just use your graphing calculator to produce a table of values and plot some additional points too if needed. Now I'd like to do some applications. Let's start with this problem, which involves a batter hitting a baseball up into the air, and the height of the ball in feet after t seconds is given by this model, that h of t equals negative 16t squared plus 140t plus 3. So part A says, what is the ball's height when the batter makes contact with it? Now t is the number of seconds after contact. So at the point when the batter makes contact, t would be 0. That's the key here. So you would just be substituting a 0 in for time. So it really would be notated with h of 0, which would be negative 16 times 0 squared, which of course is just 0, plus 140 times 0, which is 0 again, plus 3. So the answer just comes out to be 3 feet. And that seems reasonable. At the point when the batter is hitting the ball's 3 feet above the ground. Now part B asks us to find the maximum height of the ball, and when does it reach that height. So that's really the vertex we're looking for. Whenever you're finding the maximum or minimum of a quadratic function, it's the vertex is going to be the point that gives you that information. Now in this case, you see the negative 16 in front of the t squared is going to make this graph be an upside down parabola. So the graph is going to look like this basically. And we're looking for this maximum point that's at the top of the peak. So the easiest way to answer part B is to use our formula that we've developed, that to find the vertex, the x-coordinate, in this case it'd be the t-coordinate, would be negative b over 2a. Now b is 140 in this case, so that would be negative 140 divided by 2 times a negative 16, which is negative 140 divided by negative 32, which comes out to 4.375. Now that's time, so that's seconds. 4.375 seconds is how long it's going to take to reach a maximum height. Now to actually find the maximum height, we have to plug that in to find the y-coordinate. So that would be h of 4.375. So we're going to plug in a 4.375 in for time and find out what the height is at that time. Now I did that on my calculator and I came up with 309.25, and that's in feet. So that really answers part B. The maximum height is this number right here. This is the maximum height. And the time that it takes for that to happen, or in other words, when does it reach that height, is answered by this. So this is the when part of it. So that's the time. And if you put those two together to form an ordered pair, you've got the time is really your x, 4.375, and the height is your y, 309.25. That's really the vertex of the parabola. That's this top point on top of the parabola. Now to save time, I'm not going to do part C, but if you want to graph this by hand, what you would do is you'd first plot this point here on a piece of graph paper. And notice you're going to have to scale your y-axis so it goes all the way up to 309.25. So you have to scale it with some larger increment. So you plot that vertex. That's an extremely important point. You'd probably plot this y-intercept right here at 0, 3. And you could use your graphing calculator to generate a few more order pairs along that graph and plot those as well. And then just connect the graph. And it should end up looking like we set up here, an upside down parabola. The general shape is going to be something like this. It's going to start right here kind of low, right at 3, and then it's going to go, you know, up high and then come back down like this. And this would be the vertex point that we found right here. This next application I want to look at deals with a model for a set of data. Now, in this table, we are giving the average number of viewers of CNBC's Business News. And there's various different years from 2000 to 2007 given. And we're given the number of viewers in thousands. So, in this case, time represents the number of years after 2000. So in 2000, t is really 0, and then it's 2, and then 4, and then 6, and then 7. And I've made a scatter plot of this data on my graphing calculator, and you can see it over here. And I've also plotted this model that was given to us in this problem. And you can see that that model does represent the data pretty well. And what I'd like to do is find the minimum. Okay, so we want to find the minimum number of viewers over that time period, and also when that happened. So it looks like the minimum is right around here, pretty close to that ordered pair. But we're actually going to use our formula to do this. So to find the vertex, we're going to take t equals negative b over 2a again. So b is this number right here. B is already negative 84.16. So negative b, it will actually be positive 84.16. And we're going to divide that by 2 times a. So a is 10 right here. So 2 times a would be 20. So divided by 20. And I put that in my calculator, and the answer comes out to be 4.208 years after 2000, because everything's measured in years after 2000. And to find out what the average number of viewers was in that particular year, you would substitute the 4.208 in for time into the function. So let's do that. So that would be notated with f of 4.208. So you see this functional notation shows that we're going to substitute 4.208 in for the time and work out the answer. And that comes out to be 186.9. So 186.9, and that would be thousands. So what that number is, that's the y-coordinate of the low point on this parabola. Now, if you look at the data, notice it actually gets a little lower than that, 185. But remember, the model, it doesn't exactly go through every piece of data. So even though the data itself goes down to 185 right here, the lowest the parabola ever goes is 186.9. And so that would be the estimate of the minimum using the model. I'd like to go over one more application, and this one has to do with an area problem. So it says a farmer plans to use 200 feet of fencing and a side of her barn to enclose a rectangular garden, as you can see in this figure. What dimensions of the rectangle would give the maximum area? So the key word here is maximum area. And then you're supposed to find what that area is. So what is that area? So you're trying to find the maximum amount of area. So you have to express the area of the rectangle in terms of some variable. So let's let x be the width of the rectangle. So we have x here and we also have x over here. Now remember, there's no fencing needed along the barn because you already have the barn there to enclose it. So you have x here and x here, and then you have this side here, and that's going to add up to 200 feet of fencing. So this length would be 200 minus those other two sides. So minus x and then minus another x. So 200 minus 2x. So that's the key, is to represent the width with the x, and then the length would be 200 minus 2x. And you notice if you add up all three of these sides, it adds up to 200, which it's supposed to, because that's the total amount of fencing used. Now, since we're trying to maximize the area, we now have to write down the area of the garden. So the area is the length times the width. So it'd be 200 minus 2x times x, length times width. And if we multiply that together, we'd get 200x minus 2x squared. And I'm going to just rewrite that over here and put it in descending order. So negative 2x squared plus 200x. So it's a quadratic function, and here's your a and here's your b. And c is really 0 in this case because there isn't any constant term. So a is negative 2 and b is 200. And since we're trying to find the maximum area, we're looking for the vertex. The vertex is always going to give us a maximum or a minimum. So to find the vertex, we'll use our formula, negative b over 2a. So that would be negative 200 over 2 times negative 2, so negative 4. So that comes out to equal 50. So x is 50. And then if we plug that back into the original function, we can find out what the y value is, which is the area. And that comes out to be 5,000. So if we think about the units, since the units were given in feet in the original problem, the dimension for x would be 50 feet. But for area, it would be in square feet. So this is showing us that the maximum area is going to be 5,000 square feet. And that's going to happen if x is 50. Now, x is the width, so the width would be 50, and the length would be 200 minus 2 times 50, which would be 100. So if you have 50 for your x, that would be here and here. Then this other side would be 200 minus 2 times 50. 2 times 50 is 100, so it's really 200 minus 100. So that comes out to be 100. So since the problem says what dimensions, they want the length and the width. So the dimensions would be 50 feet by 100 feet. Okay, so 50 feet by 100 feet would give the most amount of area, and that area would be 5,000 square feet.